Hello, everybody. So far, in this chapter, we introduced deterministic finite automata. We defined languages that are recognized by DFAs as regular languages, and we tried to analyze the properties of regular languages. And so far, we talked about closure properties. We proved that the union of two regular languages is regular. The intersection of two regular languages is regular. The complement of a regular language is regular. And we try to prove that the reverse of a regular language is regular. And to do so, we looked at a DFA and we tried to reverse it to be a machine that accepts the reverse of the original language. The problem that we had is that this creature is no longer a DFA. In fact, it can do various things at any given point, and therefore we call it non-deterministic finite automata. It can do many things at the same time, and we need to choose which operation to take at any given point in order to reach an accept state. So before we formally define NFAs, let me give you another example of an NFA, and this will allow me to introduce another component of the definition of NFA. So this is a machine with this start state, and you can see that from the same state there is more than one transition with 0, whereas from this state there is 0 transitions with 1. So some states have more than one transition, some have 0 transitions. But in addition, we have also this notation of moving with the empty string. So at each state, we have any number of out arrows for some letter sigma, including for the empty string. This will refer to the ability to take steps without reading anything. So whenever there is an epsilon move, it means that you can take this edge even without reading any new symbol from the alphabet. The set of string accepted by this NFA, what is it? Everything that contains a 0. So if you're here and you contain a 0, then you can stay here with 0, 1 and on every one that you see. And the first time you see a 0, you can choose to take an empty string step here, the 0 string, the 0 symbol here, and then stay put. So this is, of course, not the best way to define an NFA for this language, but it helps us demonstrate how NFAs, what's the language of an NFA. And finally, there is two ways of defining NFAs, and here we're going to deviate a little bit from CIPSR. So CIPSR allows a single start state, whereas we will allow multiple start states. And the way to convert NFA with many states to a single state is using this epsilon transition. So you can define this new state, which is the start state, and now you can take an epsilon transition to each one of the previous start states, and so you can perform whatever computation you could with the many start states. So allowing many start states doesn't increase the power of the machine. You can do the same thing with a single start state. So here is another example of an NFA. And what's the language here? The language here contains two strings. The string that has 1, if you start with this start state and you take a 1, you can accept. and the string 0, 0. You start here and take 0, 0 and accept. So for example, what happens when you look at the string 1, 0? Regardless of which state you start with, there is no path that follows 1, 0. In particular, there is no accepting path that follow 1, 0. So these are the only strings that correspond to accepting path. Now let's define it more formally. Still as a 5-tuple, although we are in non-deterministic finite automata, but there will be a slight change in the notion. So a 5-tuple is an FA where Q is still the set of states, sigma is still the finite alphabet. Delta now, the transition function, takes the current state and sigma epsilon, which means sigma when you also augment epsilon to it, you add epsilon to it, meaning that you can take a step with any symbol, but also with the empty state. And now it doesn't give you a single state, it gives you a subset. So 2 to the q refers to a subset of states, and this subset can be empty or can be large. So these are all the states you can reach when reading Q and the particular symbol. So the Q is a set of all possible subsets of Q, and sigma epsilon is sigma union epsilon. Q0 is the set of start states, so now we allow more than a single state. And F is again the set of accept states. So this is how you specify formally an NFA, and we need to again define what are the languages accepted by the NFA. So a string W is accepted by NFA N if, again, there is a sequence of states, R0 to Rk, and we can write W as W1 to Wk, where WIs now are not only symbols, are symbols or an empty string, with the following property. The property that R0 is a start state, it's one of the start states, and Rn is one of the accept states, and now Ri plus 1 is a possible transition from Ri on Wi plus 1. So Ri plus 1 is contained in the set of states which is that you can reach from Ri while reading Wi plus 1. So it's in delta Ri Wi plus 1. And this holds for every I from 0 to k minus 1. So this means exactly what we said in words last time. A string is accepted by n if there exists some accepting path from the start state to an accept state. Ln now is the language that is recognized by n, which is exactly the set of all strings that the machine n accepts. And a language L prime is recognized by an NFA, and if L prime is equal L of n. So it's the same terminology we had for DFAs. Again, let's formalize this notion, and we'll do it once in lecture for an NFA. So here is the NFA that we have before. The set of states is Q1, Q2, Q3, Q4. This is the limit of what we can squeeze into the slide. Sigma is 0, 1. Again, it's the binary alphabet. Q0, which is the start state, is contained of two start states. There is Q1 is a start state and Q2 is a start state. The accept state F is Q4. So there is the set is contained only a single except state. And now let's start defining the transitions. And to define it, again, for every state and for every symbol, we're going to define a subset of states you can move to. So delta of Q2 and 1, given that you're at Q2 and you read 1, which state you can get to? Well, there is a single state. You can only reach Q4. Delta of Q3 and 1, what can you do? You cannot do anything. With 1, there is no transition, so you reach the empty set of states. Delta of Q1 and 0 contains Q3, and so on and so forth. So now we can ask, is 0, 0 in L of n? Think about it. Well, 0, 0 is easily in L of n because you can walk on 0 from Q1. You can start in Q1, walk on 0 to Q3, and walk on 0 to Q4. How about 0, 1? Well, you would like still to start with Q1. You take a 0 to Q3. But now, how can you take a step with 1? Well, you can directly take a step with 1, but you can first take an epsilon, make an epsilon move from Q3 to Q2, and now take a step with 1. So both of these strings are in L of n. NFAs are generally simpler than DFAs. So for example, this is a DFA that accepts the language which is only 1. Essentially, this is the start state. With 1, you get to an accept state. But now anything else that you'll do, you'll reach a reject state that is a sink. You cannot move out of it. And with a 0 at the beginning, you'll go to this reject state and stay there too. So this is what you need to do with a DFA, but how can you do a simpler NFA? An NFA for the same language is just that. You have a start state. With 1, you move to accept state, and now you don't need to worry about what happens with a 0 here or with a 0 later, because there are no 0 transitions, and therefore anything with a 0 or with more than 1 would not be accepted by the NFA. So it's simpler. So we have here two kinds of computations: a deterministic computation that reaches, that has a single path it can take from the start state to either an accept state or reject state. These are the deterministic computations. And we have non-deterministic computations that can be viewed as a tree. At every point, you may have more than a single thing to do, and at some point you get stuck, you have nothing to do. And then in the leaves, you reach accepts or reject. And the question is whether there exists an accepting computation. There could be for every input an accept and a reject computation, but as long as there is an accept one, then you're going to accept. So this looks much richer. And the question is, are these two computations the same or different? So are these computations equally powerful? And when you just look at this picture, it looks like non-deterministic computations are much more powerful. But as many of you know, in fact, these two models of computation can compute the same thing. So as some parting thoughts for this video, when life hands you ambiguity, you can define non-deterministic finite automata. So what we saw here is exactly an example of how good theory works. Good theory reaches an obstacle and turns it into a new notion, and it turns out to be as exciting as anything else we wanted to do. And here, it's the first time we can ask, is verifying easier than computing? So non-deterministic computations can be viewed as a verified guessing. So you have this tree of possibilities. If somebody whispers in your ear, or if you're able to guess, you will guess the right path, the path that leads to the accept state. So you're going to guess it, but then when you follow it, you're verifying that the guess is correct. And now the question is, verifying easier than computing or not? And we'll discuss it in the next video.